So by making a comparison here, we get K, which represent the radius of gyration is equal to L times the radical of 1 divided by 12. So this is the formula that we can use to get the radius of gyration for the uniform for this uniform load when it is rotating through the center. So after this one, let us go and see for Roman 2. On Roman 2, my dear student, we are going to see when the axis of rotation is at one end. Kwa kama ile axis of rotation ipo at one end, how can we get the moment, how can we get the radius of gyration? So consider two equations. Let us consider the equation number 18 and also the equation, let us consider the two equations. It means equation number 19 and also the equation number 21 and also the equation number 53 for our first topic. So equation number 21 said that moment of inertia must be equals to 1 divided by 3 ml square. But the equation number 53 here, moment of inertia must be equals to mk square. If it is equal to mk square, and we are supposed to make a comparison for these two equations, we could equate because they have both they have the same moment of inertia. Kwa tukisha equate pale, tukachokifanya yule masi atakata. Sasa masi akikata pale, tutabakiwa kumbe the radius of gyration must be equals to 1 over must be equals the moment of inertia, it means k square must be equals to 1 over 3 times the L square. But we are supposed to remove the square both sides. If we remove the square both sides, tutapata kumbe radius of gyration for the uniform load when it is rotating at one end must be equals to 1 over 3. It means it is equal to L times the radical of 1 over 3. This is how we can get the radius of gyration for the uniform load when it is rotating at one end, when it is rotating, when the axis was at the one end. So after this one, let us go and proceed for Roman 3, where we was being asked to derive the formula of obtaining the radius of gyration for the uniform ring. Sasa tunapataje formula ya kuweza kuitumia ili tuweze kutafuta radius of gyration kwenye uniform ring? This is what we are going to try to observe here. So the radius of gyration of a ring with the axis passing through it is set perpendicular to this one must be equal to this one. Kwa kitu ambacho tunaenda kukifanya hapo, we are supposed to consider that from the two equations, the equation number 2040 and also the equation number 53 here, the moment of the radius of gyration must be equals to the radius of the ring. Kwa ile radius of gyration itafanana na ile radius ya ile uniform ring. So how can we get the moment of inertia? Kwa ile moment of inertia kinachotokea ni nini? We know that for the uniform ring, K must be a moment of inertia is equal to mk square. And also the formula of obtaining the radius, the formula of obtaining the moment of inertia for that ring must be equals to mr square. Kwa tukishazi equate pale, tutakuja kupata kumbe this K must be equals to L. Kwa sababu mass atakata tutabakiwa na K square is equal to R square, but we want this values. We should apply a radical throughout. If we apply a radical, you could use the concept that if we have the same exponents, now the base they are supposed to be the same. If we have the same base, the exponent they were supposed to be the same. We should use that concept so as to demonstrate that K square must be equal to R square. Now K must be equals to R. So after this one, let us go and say Roman number 4 here. The Roman number 4, where we was asked to go and demonstrate the radius of gyration for the disk. Sasa tuende tukaangalia kwenye disk, je, moment of inertia, no, the radius of gyration tunampataje? That is what we have been asked into our equation here. So consider our equation number 63 and also our 29 for our first topic. Now we say that the radius of gyration of a disk with axis of rotation passing through its center perpendicular to the plane, it can be expressed by this one. Kwa ile radius of gyration tutaipata kwa ku consider the disk, it means the moment of inertia wa disk pamoja na yule moment of inertia wa ile disk ambayo anakuwa na involve na ile radius of gyration. Kwa tutaenda kusema kwamba kumbe, as we know that first equation, moment of inertia is equal to mk square, and also moment of inertia must be equals to 1/2 mr square. If we equate this equation, because they have the same value and both zote ni I. Now if we equate the mass could be cancelled, yule mass ataweza kuisha. Akishaisha pata tabakiwa, kumbe the k square must be equals to r square divided by 2. But we want how can we get this k? We should introduce a radical throughout. If we introduce radical throughout, we obtain that this k must be equal to r, then we times it by radical 1/2. So after this one, my dear student, we are supposed to go and see our question number 5. And our equation number A, Roman 5 here, we are supposed to go and determine the radius, it means the radius of gyration for the solid sphere. Tunapataje the radius of gyration for the solid sphere? This is what we try to demonstrate here, or to prove here. So it is the same way that we can say that the radius of gyration of the solid sphere, of the radius of the solid sphere, axis through where the radius, the axis of rotation or the center can be expressed by this one. Kwa kwenye solid sphere na penyewe tutarudi kule kule. We have to consider only two questions. Equation ya kwanza tutasema kwamba moment of inertia is sawa, we know the formula that we demonstrated there on our equation number 36, ambayo nasema moment of inertia is sawa na 2 divided by 5 mr square ya solid sphere. Ndio formula ambayo tuweza hapo demonstrate. Pia tutaliko equation yetu tutatembea nao equation number 63. So we know that the moment of inertia must be equals to 2 divided by 5 for a sphere. Then we multiply it by mr square. This could be the equation number 1. And also equation number 2, it relates with the moment with the radius of gyration. Kwamba we know that the radius of the moment of inertia must be equal to mk square. Now let us equate these two equations. If we equate these two equations, we should obtain that the k square, which represents the radius of gyration, must be equals to 2 divided by 5 times the r square. But we want the k, it means we want the radius of gyration. Now let us introduce the radical throughout. If we introduce the radical throughout, we obtain that the radius of gyration for the solid sphere must be equals to r times the radical of 2 divided by 5. So this is how you can demonstrate the moment or the radius of gyration for the solid sphere. Let us focus for Roman B here. On the Roman B, let be the distance of the axis. Let x be the distance of the axis from the center of the sphere, from the parallel axis. Kwa tutamlete huyo x awe ni distance kutoka kwenye axis of rotation kwenda kwenye center of the sphere, ambapo tuna consider ile parallel theorem, it means the parallel axis theorem. Now as we observe that we have this distance, it means kutoka kwenye axis of rotation ambayo ni AB, where the center is originated, mpaka kwenye ile parallel axis kama tunapojaribu ku observe pale. Now we obtain the moment of inertia along to the xy, kwenye xy is equals to the moment of inertia along to the AB, ile moment of inertia iliyopo at the center, then we add by the distance ambayo ina exact kwenye parallel axis series, which is equal to mx square. Now we are supposed to make this MK as we are supposed to demonstrate our formula. Now we could say that instead of writing IXY, we should substitute equals to MK square. Then is equal to the moment of inertia along to AB must be equal to 2 divided by 5 mr square. Then we add by mx square. So the aim of this is to get the moment, the radius of gyration. Radius of gyration hapo ukimake the subject, because we have the same m. Kwa ukimake the subject tutapata kumbe radius of r square must be equal to 2 divided by r square, then we add by x square. Kwa sababu huyu radius of gyration ni sawa na r. Kwa tukimwekweti pale ndo tutampata rx is equal to r divided by 3. So we could conclude by saying that the distance of the axis from the center of the sphere is equals to r divided by radical 3, my dear students. So by saying that this will be at the end of our session here. Now I would like to invite you again for another session. I wish you all the best. Have a nice moment.